Okay, let's dive into this laser-focused explainer on a specific, high-yield GCSE math problem. Today, we're completely demystifying Question 8 from the Edexcel November 2023 higher tier paper. We're going to break down the exact step-by-step logic you need and look directly at the official mark scheme requirements.
So, how do you actually secure two easy marks on error intervals? It's a really common format that honestly frequently trips students up. The terminology can feel kind of abstract when you're forced to work backward, but I promise you by the end of this explainer, you'll have a foolproof, repeatable method to lock down full marks whenever this pops up on your paper.
And this brilliantly illustrates exactly what we're up against. Here is question 8 directly from the exam paper. It reads, a number x is written correct to two significant figures. The result is 1.9. Complete the error interval for x. There are two marks up for grabs here. It looks simple enough, right? Just a couple of numbers to fill in. But to execute this accurately, we need to strip this back to the absolute basics of what these numbers actually represent.
Before we calculate a single thing, let's set a rock-solid foundation. What actually is an error interval? Well, an error interval is simply the range of all possible values a number could have been before it was rounded or truncated to a given accuracy. Think of it like a window of possibility. When you see the number 1.9, you know that the original unrounded number wasn't necessarily exactly 1.9. It could have been slightly smaller or it could have been slightly larger. Our job is to find the absolute minimum value it could have been, and the absolute maximum boundary it could reach before it would round up to the next number.
To find that window, we've got to look really closely at the number they provided, 1.9. The question explicitly states this number is rounded to two significant figures. The digit 1 is our first significant figure, and the digit 9 is our second. Therefore, the degree of accuracy is governed entirely by this last significant digit. And where does that 9 sit? It sits right there in the 10th column. This means our number has been rounded to the nearest 10th or to the nearest 0.1. Understanding this place value is absolutely crucial. It's the key that unlocks the entire problem.
Let's move to and see how this builds into our actual calculation. There's a strict three-step process you want to follow here. Step 1, like we just determined, is to identify the place value of the last significant figure, which gives us our degree of accuracy, 0.1. Step 2 is the most vital mechanical step. You must have that degree of accuracy. Half of 0.1 is 0.05. And finally, step 3, we take that halved value, the 0.05, and apply it directly to our original rounded number, 1.9, to find our upper and lower boundaries. Okay, let's execute that third step, starting with the minimum possible value, known as the lower bound. We take our original number, 1.9, and we subtract our halved degree of accuracy, which is 0.05. So 1.9 minus 0.05 leaves us with 1.85. If you think about it logically, if you have the number 1.85 and you're asked to round it to two significant figures, that 5 in the hundreds column dictates that we round the 8 up, landing us perfectly back at 1.9. So 1.85 is for sure the absolute lowest number that x could possibly be. So, the crucial point is exactly how the examiner awards you for this. Quoting verbatim from the official Edexcel mark scheme, you earn a B1 independent accuracy mark for, quote, 1.85 in correct position. That means it must be written on the left side of the inequality, representing the lower bound. Find the place value, half it, subtract, and that's your first mark totally locked in.
Now we need to set up the top end of our interval, the upper bound. We use the exact same logic, but instead of subtracting, we add. Take our original number, 1.9, and add our halved degree of accuracy, the 0.05. 1.9 plus 0.05 gives us 1.95. This establishes the ceiling of our interval. Now, I know your brain might be screaming, wait a minute, 1.95 rounds up to 2.0. And you'd be completely right. That's exactly why the inequality symbol in the question is the real hero here.
Let's look at the baseline requirement for your second mark. The mark scheme states you earn another B1 mark for, quote, 1.95 in correct position. That means putting 1.95 on the right side of the inequality. Writing down 1.95 is the standard expected method for displaying the upper bound. It defines the strict boundary that the value of x can approach but never quite touch.
Now, what's really interesting about this slide is the highly specific alternative upper bound decimals accepted by the mark scheme. Examiners know that mathematically astute students might overthink the strict less than boundary. Because x must be strictly less than the upper bound, some students will write the absolute highest decimal that still rounds down to 199. Because of that, the mark scheme explicitly accepts 1.949 with a dot over the 9 indicating it's a recurring decimal, or 1.9499 with an ellipsis. You will still get the full mark for those, but standard practice remains writing 1.95, as that strict less than inequality symbol does all the heavy lifting for you.
Bringing everything together, your final, fully correct answer line should look exactly like this. 1.85 is less than or equal to x, which is strictly less than 1.95. This complete statement beautifully defines the error interval. It says that x can be exactly 1.85, or literally any number greater than that, all the way up to, but not including, 1.95. It's clean, it's mathematically precise, and it guarantees both marks for question 8.
Error intervals are just one application of understanding bounds and accuracy. So I'll leave you with this. If you can master significant figures here, identifying the place value, having the accuracy, and confidently applying it, what other rounding marks can you guarantee on your next paper? This exact step-by-step logic applies to calculating maximum and minimum areas, working out bounds and complex formulas, and so much more. Take this logic, apply it rigorously in your revision, and go secure those marks. Thanks for joining this explainer, and I'll catch you in the next one.